Here is an explanation of the steps we took to create our circuit. We will also explain the circuit drawing and play demos of our progress and final circuit. This is how the transmitter works with a 100 Hz signal. This is how the transmitter works with music playing.
So that's how I currently have it set up, and then I thought if I just put a potentiometer over that one and a potentiometer over that one, so these are both in the range of 0 to 10. I thought that would just make it so.
For the transmitting circuit, we have two inputs. The first is an aux cable that is connected to a capacitor to block out the DC current. Then it is connected to a potentiometer, which is used to adjust the volume of the aux within the circuit. The other input is a mic input. The mic is powered with 4.5 volts and is connected to a non-inverting amplifying circuit where the resistors allow a gain to make it louder. The mic input signal then goes through a high-pass filter, which was designed to block out any frequencies less than 60 Hz, which is the environmental frequencies caused by lights, so it reduces noise within the circuit. The mic is also connected to a capacitor to block out the DC offset, which comes from powering the mic. These two inputs are combined in a summing op-amp. All of the op-amps that are used are powered with 4.5 and negative 4.5 volts, which comes from a voltage divider, which also defines the virtual ground. The output of the op-amp is then connected to another capacitor to block out any DC current, and then connected to a bias T. The bias T adds a DC offset for the laser, making it brighter so it can be seen at further distances. For the receiving circuit, the photodiode is connected to ground and then a capacitor, which allows for only the AC signal from the laser to flow through the circuit. Then the signal goes into an amplifier to make a stronger signal. A parallel op-amp is then set up to increase the current in the circuit, allowing for more power to go through the speaker. This is important to make the speaker louder. The positive input for the first op-amp is connected to the positive input of the second op-amp, and the second op-amp is set up as a buffered circuit to hold the same voltage and current values as the first one. The two outputs are connected to resistors and then to the same node where the current is summed. Then a capacitor is added before the speaker to block out any DC input that may flow through the op-amps, and the speaker receives the amplified AC signal.
These are oscilloscope measurements taken from our circuit. The graph on the left is the input of the laser through the aux cord and microphone. It shows a sine wave at about 1,000 Hz frequency. The graph on the right is the output of the speaker. It also shows a sine wave at about 500 Hz frequency. These are the voltage measurements from our circuit. From this table, the measured AC voltage of the laser was 0.5 volts, and the desired voltage was 1 volt. The desired DC voltage was 3.5 volts, and it was measured as 2.43 volts. However, the laser was still bright enough to transmit the signal effectively. The desired speaker voltage was a voltage greater than 2 volts for the sound to be loud enough. This was achieved since the measured voltage across the speaker was 2.21 volts for our receiving circuit. The voltage across the photodiode was measured to be 0.183 volts, although the desired voltage was 1 volt. This still allowed the diode to receive the laser signal. This is a screenshot of the sound output measurement of the speaker while music was playing. It was measured at about 3 feet from the speaker. From this measurement, the output was about 74 decibels, and the average sound output was 65.1 decibels.